Hello and welcome to the Open Heat Transfer course Conduction. In this video we will show you a short example of a clinical thermometer and how to calculate the temperature rise over time. For this we will look at the lumped capacity model that we have learned in the last video. Let's start with a physical understanding of this clinical thermometer. This is a thermometer made out of glass with a mercury cuvette here in front, and the mercury will expand due to the rising temperature and its volumetric expansion, and due to this expansion we will have a changing scale here, and from that scale we can read the temperature. So what are the given parameters? So let's look at the size of the object. So we will look here at the mercury tip. We have a specific length and diameter from which we can calculate the total volume of the mercury part. Let's assume an initial temperature of 20 degrees Celsius, and the mercury has the following properties like heat capacity, a density, and the thermal conductivity. Now, how can we measure that? The child must measure its body temperature now at two different instances of time. So let's say we start after 40 seconds with the first reading. So we read the temperature of 34 degrees Celsius, which is not that high. So we can guess that the child is not having fever, even a much too low temperature, but waiting a longer time for T2 equal to 100 seconds, the temperature has risen to 39 degrees Celsius, so this is already a fever temperature. Now the question is, what is the right temperature? How high is the fever, and how long should we really wait to get an accurate reading of it? What we don't know, and what we have not given here in the parameters, is the heat transfer coefficient alpha, which we have somehow to determine. And then, of course, how long does it take to determine the temperature with a precision, let's say, of 0.1 Kelvin? Finally, what are the assumptions, and are the assumptions valid that we did for calculating the problem with the lumped capacity model? How high is the fever? So, first question, let's look at the lumped capacity model. We have here the dimensionless temperature, which is equal to the temperature depending on time minus the initial temperature divided by the fever temperature minus the initial temperature. And this value goes from 0 initially when the temperature is equal to the initial temperature, up to 1 if the temperature has risen towards the fever temperature. And this is expressed here by the exponential function 1 minus the exponent of the expression above. This one is depending on the time. Now we can combine all these parameters here in the unknown value m. The problem is, although we know the area, the volume, and the properties, we do not know the heat transfer coefficient alpha. So we can name this the unknown parameter m. Now, let's rewrite the equation. We will bring the 1 to the other side, and then we can expand the 1 by Tf minus T0, and if we do that, minus T and minus T0, T0 will fall down, and we will be left with T fever minus the temperature depending on time is equal to the exponent of minus the unknown parameter m times the time. If we want to determine this unknown parameter m, we need to take the logarithm here of our expression, and we have now an explicit equation for the unknown m, but what we don't know is of course the fever temperature. But what we know is that we have two different readings. So we have the one reading for the temperature time T1 and the other time T2. We can utilize these two information and calculate then the unknown values. But the problem is we cannot do that explicitly, because if we rewrite this equation here, we can see that the ratio between T1 and T2 is equal to the ratio between the two logarithm values with the unknown temperature T fever. Because we cannot easily make an explicit equation out of that, we will use an iteration process, and let's start with the good estimate of a fever temperature of 40 degrees Celsius. So if we put in the times T1 divided by T2, we come up with a value of 0.4. If we plug in here the 40 degrees Celsius for the fever temperature, we will end up here on the right side with a value of 0.402, which is a good match between those ones. So let's assume that the fever temperature is 40 degrees Celsius. It was like a lucky guess right now. Now, let's calculate now with the known fever temperature of 40 degrees Celsius, the unknown parameter m. That's what we can do here with one of those equations. We plug in all the values that are given, and we come up with the value m equal approximately to 0.03. In the next step, we would like to calculate the heat transfer coefficient alpha. For this, we will look at our constant m that we have introduced, which is equal to the heat transfer coefficient times the area divided by the volume and the two properties, the density and the heat capacity of the mercury. This value was approximately 0.03, from which we can now calculate the heat transfer coefficient alpha by using the appropriate values. So what we come up with is that the heat transfer coefficient is equal to 58.8 watt per meter square Kelvin. Now, with knowing the heat transfer coefficient, we can also calculate the Bio number, which will tell us if our assumption of the lump capacity model is correct, which means that the temperature inside the mercury is nearly homogeneous, which requires the Bio number to be much smaller than 1. So let's plug in the values for calculating the Bio number. The relevant length scale is the half of the diameter, so that's the distance the heat needs to travel inside the object, and so the heat transfer coefficient times the relevant length divided by the thermal conductivity of the mercury will give us a value of 0.013, which is much smaller than 1, and as such the assumption of the lump capacity model are all valid. Now let's come to the question C. How long must be measured to determine the temperature within an accuracy of 0.1 Kelvin? Let's look at the diagram what happens in time. So we see here on the time the change of the temperature. We start with temperature of T0 and we will approach the fever temperature T with time. Now we would like to be within 0.1 Kelvin close to the object's temperature T fever, and this deviation thus needs to be here 0.1 Kelvin. And here is the measurement time that we need. So let's look at the equation. We can calculate Tm using our equation rearranged with 1 over the parameter m times the logarithm of T fever minus the actual temperature, and the actual temperature is 0.1 degrees smaller than the fever temperature, which then gives us that Tf minus T is equal to 0.1. If we plug in those values, we can calculate the time, and this time is 176.6 seconds. Let's finish this video again with a few questions. So for safety reasons, of course, mercury thermometers are no longer available. Thermometers filled with alcohol are also hardly used anymore. Why? What are the disadvantages of these measurement instruments? So for sure, the time that it's needed to calculate the proper temperature is relatively long, especially if you account for the fact that alcohol has a much lower thermal conductivity than mercury. The time will be even much lower. And as such, now with the digitalization of measurement devices, it's of course a standard to have a digital thermometer. And the question that we have now is, how can the body temperature determined effectively or in an efficient way using a digital thermometer? I will answer this question soon. If you want, you can also think of it and stop the video. How can we calculate the temperature TF with a digital device? The digital device allows to store different measurements at different instances of time. And with two values known, we have seen in the prior calculations that we can calculate the unknown parameter m, and we can iteratively also calculate the fever temperature TF. If we use multiple values, then we can not only calculate the temperature TF, but we can also calculate the deviations that are expected to the temperature TF, and as such we can also have criterion for stopping the measurements. And that is the reason why we can measure much better using a digital thermometer. Thank you for your attention, have a nice day and stay healthy.